We okay? We okay? Yeah, that's okay. I mean, it's been over 10 minutes, so we'll. It's their problem, not mine. So y'all want to do one? Which way y'all want to go? So let's do binary to hex. We won't try to get too big, and I'll spread it out. In fact, what I'll do is I'll group it into fours to make it a little easier for us to do. So let's convert this to hex. So until you learn the patterns, you can do what? You can match it. So what would this be? What would this be? What would this be? B, B, A, 1. And all it takes is learning or memorizing 16 patterns. And I just think about, in elementary school, we learned those multiplication. Why did you learn multiplication tables? So you wouldn't have to add. So all multiplication is nothing. In fact, when microprocessors first came out, they could not multiply. All they could do is add and subtract. So we had to write programs to make them do what? Multiply. And that's when I really learned, multiplying is repetitive addition. So 5 times 5 is 5 plus 5 plus 5 plus 5. But instead of us doing it, we learned what 5 times 5 was, right? You understand? So we wouldn't have to add it out. So that's why we learn multiplication tables. So all you have to do here to go between these is just learn between these nothing. We don't want to make it decimal between hexadecimal and decimal. That would be hard, isn't it? Uh, so let's take this to decimal using base 16. So this is 16 to the 0. So I'm going to erase the binary number. Everybody okay? So this is 16. This is what we would have to do to go from so this is 16 to the 0. This is 16 to the first. This is 16 squared. This is 16 to the third. So I would get everything in decimal. So this will be 11 times 16 to the third. What's 16 to the third? You got it on your chart right there. 4,096, right? Plus 11 times 256. That's 16 squared, right? Plus, I can do that in my head. 10 times 16 plus 1. I know this is odd, so this is pretty easy. If that's odd, your decimal number is going to be odd. But now you got to remember that that B is odd, right? D is odd, right? And F is odd. So you have to know that. So we should expect an odd decimal number here. So this is what we'd have to go through to go from hexadecimal to decimal. I wouldn't do that. I would take it to binary and go from binary to decimal is what I would do. Because now you have to have a what? You have to have a calculator. Go from binary to decimal. We can come over here and let me get out of this. I'm gonna keep this. And I'm gonna go to Windows Calculator, and this is Windows 7 on this computer. Come on, pop up. Oops, there it was, Rich. And then up here under View, I'm gonna go to Programmer's Calculator. I got about 3 versions of it here, and there it is. So I could come over here and I can select hex, and then I can say B. Now notice the keys changed over here. BB A1, and then I can just come over here and flip it over to decimal, and that's what this answer. So if I was going to go from hexadecimal to decimal, I would use a calculator. But if I was going to go from hexadecimal to binary, I wouldn't use a calculator. If I didn't have a calculator, I'd go from hexadecimal to binary, and then I'd use the powers of twos, and then I would add them together. That's the way I would do it if I didn't have a calculator. So this guy does octal. I flip it to octal. So now I can look at it, and so that's the number in binary. That's the number in octal. That's decimal. That's what is equal to hex. So this calculator just basically rips through those, no problem at all, right? And how do I switch it into the Windows 10 calculator? This is still running Windows 7, even though I got to update it. Windows 7 shows you the other bases anyway. So even though you can switch between the two, but see how my keys changed? So A, B, C, D, E, F, and I got 0 through 9 over here. I can multiply with this, can I? Nope, the multiply's gone. So I think calculators that would get you multiply numbers and divide X numbers. But look, words, double words, quad words. So right now it's showing me a quad word. So we know what that means now, right? So what's a byte? Double word is 32. A quad word is 64. So even the calculator, you know this. Oh, that would be a. We're not going to explain this yet. Oh yeah, this shows the byte. This shows that. I don't know why. I can't see down here. Down here it shows you the number of slides, but my timer's down below that. Okay. Thanks for letting me know. And it's being recorded too, by the way. So let's count in hex. Like, I mean, it's a legal question, but I don't keep up with the number of slides. I just go. So let's count. 0, 1, 2, 3, 4, 5, 6, 7, 8. What comes next? A, B, C, D, E, F. I've run out of combinations. What comes next? I gotta keep counting. 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. What comes next? 1 A, 1 B, 1 C, 1 D, 1 E, 1 F. That's just like it. So I'm counting in base 10. I go. If I'm counting in base 10, I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to keep counting. What do? We add a 1, put a 0. Well, we're doing exactly the same thing. So 1F, then what would be next? 2, 0. Just like you get here. So I'm gonna go from here. Then I'm gonna go 1, yeah, I'm going to go 10, 11, 12, 13, 14, 15, 16, 17, 18, 18, 19. I don't jump over here. What do I do? I increase this by 1 because I hadn't run out of combinations over here. And then I go 20. Well, over here, this is not 20. This is 20. This is actually 32. That's 32. I've counted to 16 twice. This is what you got to learn, that 10 in any base is the base. So 10 is 16 in base 16. 10 is equal to 2. And you keep counting until I get up to what here? Until I get to F. Yeah, so I'd go 2 1, 2 2, 2 3, 2 4, 2 5, 2 6, 2 7, 2 8, 2 9. What comes next? 2A, good. 2B, or not 2B, right? 2C, 2D, 2E, 2F. Then I do what? 30. And then I keep going until I got up to FF, which is 255. I've run out of combinations. What would I do? Put another 0, that, and then I'd start the whole thing over again. Hmm? But this is counting in hexadecimal, and this is what people, and the problem we have is what? We see this, we see that as a what? 10. And it's not a 10. It's 10 base 16. This is 16 to the 0. This is 16 to the first. That is equal to 16. That is equal to 30. If I was to convert this to decimal, that's equal to 32. So what you got to know, and this is why the hexadecimal number system is a lot more efficient than the decimal number system. I can represent bigger numbers with fewer digits because the decimal number system only got 10 combinations per digit. The hexadecimal number system, I got 16. So I can represent large numbers with fewer digits. And in plus, I can go between what real fast? I can go between what? Binary and what? Hexadecimal. When I come over here, I want to find out what the address for the video card is, the actual binary address. Yeah, I can come over here and I can come over here and I can look at all programs. Where'd I go at? Accessories. Then I come back and go what? System tools. And I'm going to go down here and get system information. And these are addresses. Everything in the computer is assigned to what? A binary address. And what bus does it use to select everything? It's called what bus? Address bus. So this guy right here's got an address bus. These go flying out, and then it goes to a circuit called the address decoder, which is basically, this is just a circuit that's looking at the address bus. And when it sees this address come out, it lets the data flow through to whatever port or whatever memory location we're addressing. So here's I/O right here. Here's the I/O address in these computers. So I'm going to go to hardware resources, I/O, input, output, and there's the address map right there. But what base is it using? So let's see, where's the keyboard at? There's y'all see the keyboard? See, here's the speaker. That's that thing that beeps at you. It's at 6.1, but that's a hex. That's a hex. Y'all understand? It's not going to give it to me in binary. So my computer displaying all these at what? We can find them. Let's see. Programmable interrupt controller, which I don't know. Direct memory access. That's the guy that's refreshing our memory for us. Here's the chipset, motherboard resource, PCI, but good gracious, I didn't look. Let's see. I'm looking for, that's the system timer. That's the guy that's keeping up with the time. Here's the speaker. Here's the keyboard right here. It's at address 64, but that's hexadecimal. But it's displayed. Here's memory. Memory shows up. Memory looks, so I could take that. If I needed to, I could do what? I could convert it to binary. But just think about if the computer tried to display that address for me in binary. Each one of those digits are each one. Am I gonna have to separate y'all? Okay. Each one of my digits, each one of those digits is what, 4 binary bits. So if my computer is trying to convey this information to me, if it tried to do it in binary, it would be, if it tried to do it in decimal, it wouldn't mean anything because it's not a decimal address, it's a what? It's a binary address. So that's why they don't give you addresses in decimal because they're not decimal addresses. That makes sense. That means if these computers are going to display large binary numbers, they're not going to do it in binary. They're going to do it in what? They're going to use it in a higher level base, like base 16 or base 8. Base 8 is still supported by PLC. These computers, they don't care about base 8 anymore. And why base 8? Because the first processors, well, actually the processors only used 4-bit data buses. Then they went to 8-bit data buses. And that's when the octal number system really came into play. It was when they came out with 8-bit processors. But now we're dealing, what's the processor size? The data bus size now, 64-bit. 64-bit. This is a 64-bit operating system. So that means this guy can transfer. It's actually got a 128-bit data bus because it does two quad words at the same time in loads of caches. So you're talking about a lot of pins. We're still dealing with a. I think the address bus, I think is still around. I don't know. I'd have to go back and look. We could look. So the biggest address we have goes right here. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that's 64 bits. So the address bus is 64 bits now. But I could take it if I needed to and convert it to what? The actual binary address that goes with the address bus. But why? Y'all probably didn't even know this was there, right? Well, we'll talk about the interrupts. If you take PLC2, we'll learn about that. There's all the interrupts assigned to the computer. An interrupt is a way that a device can get the processor's attention. So I hit a key on the key. So how often does this computer look at this keyboard? Only when I hit a key. Does that make sense? And then what it does is it generates an interrupt. So that would be just like in a formal classroom environment where I didn't ask anybody anything. I didn't let you. You had to do what? Raise your hand. And what did you just do? You interrupted me, right? And that's the way these computers work. So all devices have these interrupts right here. Processor can interrupt the processor, the ThinkPad, the keyboard, the clock is keeping up with time, uses that. So, and then conflicts. Hopefully, we don't have any conflicts in the computer. Well, we got multiple things trying to use this guy, but that's okay. Octal number system. We count in octal going from 0 to 7. Everybody okay? But instead of using 4 bits, if I go to decimal, I'm going to use how many? And that's a little easier because these pass because you don't go from 0 to. So we had the number a while ago. I think I might have lost it. Let's see. No. And of course, PLCs, the first numbering system they used was octal, high level numbering system besides binary. Okay. So if I wanted to convert this into hex, what would I do? Starting from the least significant bit, I split it up into 4s, right? Then I would pretend there was a 0 over here. And what would this be? 5. What would this be? A. What would this be? F5. If I wanted to go to octal, are we okay? Are we okay? If I wanted to go octal, I would split it up into groups of threes. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. This is still equal to a what? 5. What's this equal to? 5. This is a 3. This is a 6. That's a 5. 1, 2, 3, 4, 5 digits. 1, 2, 3, 4. So you can see that the hexadecimal number system is more efficient because we get 16 combinations. So to go from octal to binary, we would use groups of 3, right? You understand that? If we're going to hexadecimal, we're going to use groups of what? 4. If I'm going to base 10, I got to do the 1, 2, 4, 8, 16, 32 stuff, right? Everybody understand that? Are we okay? So octal is what's the base? Octal 8 and base 8. Okay. Everybody okay? 4s, 3s. So if I came over here and said 1936, what base cannot that not be? What bases can that number? The biggest thing you can have numbers is the 7. And this is the problem we have. What base could that be? Any of them. We had to make a 0. I think that's one of the questions, by the way. What number system can this not be? Binary to octal. Y'all okay on that? Everybody, anything? Anybody want to say that? Yes. So you say sure. Okay, so we'll split them up. This is base 2, so I'm going to identify that as base 2. So what would this be in octal level? Got it yet? Everybody agree with that? Everybody okay? Did you do that, Derek, or you texted in my classroom back there? Mhm. Are we okay? Huh? Don't know. Ain't got there yet. So hex, we'll take the same number and split it into groups of what? Fours? Looks like 2DD, right? Your octal? You just see them in your head. We can always add zeros over here, and that don't change the weight of your number, right? We can't put zeros over here. That's why we always start with the least significant bit and move toward the first. And what you're trying to do is get it in three groups. But most people, or after a while, you learn to see the zeros out there, and you don't have to add them. So if I was going to go to hex, what would I do? Starting with the least significant bit, 1, 2, 3, 4. I divide it into nibbles, right? 1, 2, 3, 4. And then what I do in my head, I just do that. But what you got to do, there's two zeros out there, right? So this would be a 2. This would be a what? D, and that would be a D. And then if you learn your multiplication, 16 multiplication tables, uh, you can convert this over. I don't know how far does like multiplication table there. How far does that go up? And, you know, did I give you powers of 16s though? How far did that go from power 16s? I didn't give you any powers of 16s on there. Okay. 16 to the 10th. So this would be 16 to the. This would be 16 to the 0, 16 to the first, 16 to the second. So this would be 2 times 16 squared. What's that? 256, right? And then this would be 13 times 16 plus 5. So once if you learned your 16 multiplication table, it would actually be easier to go from especially if you go to 1, 2, 3, 16, 13, 4. And I just went ahead and converted this to the decimal. So I know this is a 13. Now 2 times 256 plus 13 times 16, 5, and I converted that to decimal. But you You have to know those 16. Yeah, y'all don't have to do it. Are we okay? Well, what we're doing is we're taking this. So this is in the 16 to the, this is 16 to the 0. This is 16 to the first, and this would be 16 squared. What we do is we take, we want to get it to decimal, so we're going to put everything in decimal. So 2, there's the 2, I'm sorry, plus 2 to the 6 times 2 to the 16 squared, which would be 256, right? Plus D, what's D equal to in decimal? 13 times 16 to the first, and then plus 5. And then this is the way we could go directly from hexadecimal over to decimal without a calculator. It's something you're not going to have to do. It's just that I just want to show y'all that, right? You understand? So, but like I said, normally we do not use decimal. Use decimal to represent parts, to represent counting in octal. So let's count in octal. So let's start off what? 0, 1, 2, 3, 4, 5, 6, 7. I've run out of combinations. What would I do? 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 3, 0, right? We keep going until we got all the way up to 77. Then I'd go 1, 0, 0, right? You understand? And we'd start the whole thing over. And the problem is that we have is in our brain, we don't see this as 3, 0. We want to see it as 30. And that's the problem we have. Right? Huh? Well, the problem is that we've been dealing with base 10 how long? We probably started learning to count before we even got into elementary school. Our parents probably started playing around with us, right, and doing that, you know, the alphabet. So the problem we have is that, and this is one of those situations where learning something new is made difficult by something you already want, you already know. It's real hard, you know, for us to do that because the way our brain works in decimal. Yes, that we see that a lot of numbers we can add together. We definitely can count in base 10. But we're using the same feature. We're just applying it to our day. So normally we don't use hexadecimal to represent large decimal numbers. We use hexadecimal to represent, so we can go directly from binary. We can represent real large binary numbers with very few digits. And it makes it easy for me to convey these numbers to you without error. The only problem is if I come up here and say this, so normally if I come up here and I said 2B73, you'd say, oh, that's hex. But if I come over here and I say 2379 and I put back base 16, you want to see it as what? A decimal number. That's what you want to see it. You want to see this as 2,379 when there's no way in the world it is that because it's base 16. It's 2379. Normally we're not even supposed to say it like a decimal number. And it would be a big number, right? So this would be 16 to the 0, 16 to the first, 16 squared, 16 cubed. So this is going to be 2 times 4,096 plus 3 times 256 plus 7 times 16 plus 9. That's a big number, but it's very few digits. So if we were to learn how to count in hexadecimal instead of decimal, we could have bigger numbers with fewer digits, right? You understand that? So hexadecimal is a lot more efficient than decimal. So we talked about numbers. We got one more thing we got to make sure we get out of the way. We talked about numbers, but I've got to be able to represent more than numbers, right? You understand? So I'm up here counting and typing in a Word document, and those are not numbers; those are letters. But yet the computer only understands binary. So what that means is we've got to start using codes. A code is when we use one thing to represent something else, right? Y'all understand that? Okay. So we have 3 codes or 4 codes that we'll look at. We're not going to look at EBCDIC. EBCDIC is not extended instruction binary code. I can't remember what it stands for. This was originally one of the codes that was used by the old IBM mainframes. But nobody uses that anymore. What we use is we either use a code called binary coded decimal, or we're going to use a code called American Standard Information Code for Information. American Standard Code for Information Interchange. People call it ASCII. We'll look at Unicode, which is used by the internet and everything that Microsoft puts out. We'll look at another code called a gray code, which is a high-speed counting code. Okay? I know these lectures get long, guys, but we lost a whole day with them. So, BCD, coded decimal, American Standard Code for Information Interchange, is also called what? ASCII. So it's a true acronym. What's an acronym? It's when we take a phrase and we take the first letter. It's not abbreviation. It's when we take the first letter of each pertinent word. So a lot of times we'll leave off the fours and that kind of stuff and stuff like that unless it makes a word. And we use that to form another word. And now over time, that's not true anymore. So most people don't call these Southeastern Conference, they don't call it SIC, right? They call it SEC. So in computers, there's a lot of them. We still call them acronyms, but we call them acronyms when they're not true acronyms. To be a true acronym, they got to make a what? A word. So ASCII, and that's a true acronym. But it actually stands for what? American Standard Code, and we dropped the 4 because it's not a pertinent word for information interchange. EBCDIC, Extended Binary Coded Decimal Interchange. The book calls about this. The book calls it extended ASCII, but that is totally false. I need to take rid of that slide. In Unicode, we'll look at this. Are we okay? So binary coded decimal. This gets people totally confused. Because binary coded decimal is a code. It's not a numbering system, it's a code. So how many combinations can I have with 4 bits of binary? 16. How many combinations can we have with a decimal? With a decimal number system? We can only have what? 10. Everybody understand that? Decimal. So what we have with 4 bits of binary, I can have 16 combinations. With each digit of decimal, I can only have 10. So what we do with BCD, it is not a numbering system, it is a code. And what we do is we directly represent the decimal numbering system with 4 bits of binary. but somebody's going to try to do this. So I'm going to say 9,863 base 10. Then in BCD, this would be 9. This would be 8. This would be 60. That would be 3 BCD. Now, somebody in this class is going to try to go from decimal to binary by using this technique right there. That only works with hexadecimal. Because what I'm doing is I'm sacrificing 6 combinations to represent this. This does not go 1, 2, 4, 8, 6. This goes 1. Some people call it the 1, 2, 4, 8 code. It don't go 1, 2, 4, 8, 16, 32. It is not a numbering system. It is a code. It's called binary coded decimal. We're using 4 bits of binary to represent each decimal digit. It's BCD. You're right. I did that just to see if y'all was paying attention. I don't know where I got that from. That would actually have been a 9, right? So this is BCD. What does BCD stand for? Is it a numbering system? No. So what? It's a code. Everybody understand that? Pretty easy, right? Not too bad. Who's going to mix this up? Who's going to go from decimal and they're going to go to BCD and they're going to call it binary? Somebody in here is going to do that, right? By the way, we got a worksheet for y'all. Are we okay? Huh? Are y'all okay? I wish y'all would make me a liar. 0, 1, 2, 3, 4. I think this slide's mixed up, by the way. And that's it. That's all we can do with BCD. I think this guy keeps counting. It does. And that was hard to do, guys. I'm not going to go back and redo that. BCD, binary coded decimal. We have 10 combinations. So we sacrifice 6 combinations down here, right? It is not a weighted number system. It's a code. Y'all understand that? It's not a numbering system. It's a code. BCD is a code. It's not a numbering system. It's not weighted. A numbering system goes in powers, right? 10 to the 0, 1, like that. It is not a numbering system. It's code. BCD is not a numbering system. It's a code. You'll see that in red, right? Okay. What's that? So what would be the BCD code for oh, I'm giving a decimal number. Let me give you a decimal number. So what would be the BCD code? One, right. That's not a 5. What that's a 5. It's the first. In fact, if you look at your BCD, it's got the BCD out to the side, right? It says yes, 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 no, no, no. Nah, you go there. Go ahead. Yeah, that's BCD. It's decimal. It's directly representing decimal numbers. So decimals on decimal digits only go from what? 0 to 9. But you have to look at when you look at that chart. We're sacrificing the most significant numbers, right? So we're sacrificing 10, 11, 12, 13, 14, and 15 on a hexadecimal number. You cannot go from decimal to binary by using groups of 4s. You have to do the subtraction method, right? You understand? Lay out your table 1, 2, 4, 8, 16, 36, 64, like that, and do the subtraction. That makes sense. But somebody is going to do what? They're going to go directly from decimal to binary by using groups of 4s. Sound like you? It don't hurt on the worksheet. It don't hurt now, but by George, it's going to hurt on the test. Are we okay? All right. Gray code. Gray code is accounting code. The book's got this totally wrong. So the problem we have with counting is that we have counters, and what happens is it's got to propagate. So the more propagation is how long it takes to count to respond to a change in input. So if it took 10 nanoseconds for every count, that means the first one would be 9 nanoseconds. The second one would be what? 18. The next one would be, right? And it would keep increasing. So the problem we have with the binary code is that for every digit that changes, we would have to have that propagation delay. So if I was counting in binary, let's see if I've got that in here. So if I was counting in binary, so here's binary over here. So I'm counting from 0 to 1. How many bits changed? So how many bits changed when I counted from 0 to 1? 1. How many bits changed when I counted from 1 to 2? 2. Right? This one changed to a 0. How many bits changed when I counted from a 2 to a 3? 1. How many bits changed when I counted from a 3 to a 4? 3. So what happens is that we would have different propagation delays for every count, right? You understand that? And here only 1 bit changes, here 2 bit changes. But this is the problem we have with these counters, is that they were not able, the PLC counters were not able to keep up with some real high speed demand. Right now, this is the primary way we used to sense the motor. We call a increment encoder. And like the encoder we got back, it's got 1,800 pulses per revolution. So I mean, if you're running 30 RPM, that would be 1,800 times 30. With a, right, you understand? We got disk drives out there spinning on our hard drives running at 7,200 RPM using coders that running at precisely the right speed. So the problem we had is a regular counter just could not keep up with these devices. I've seen these lines, a can manufacturer, where these cans are going by and they look like a what? They look like one can because they're doing what? They're moving so fast. And just a regular counter, a PLC, a software counter, just could not keep up with that. So what happened is we started losing count. So what they said, okay, what if we come up with a code where only 1 bit changed for every count? And we had a method of converting it over. And then what we would do, high-speed counters, then we would just read them every once in a while. Does that make sense? But it would never lose a watt. Never lose a count. So these are called gray codes. Gray code is a method. So here's gray code. This is the way we do it, by the way. We do what we call an exclusive OR. So the way it's converted is if we see can you see a binary gray code? So if I had a binary count of 10110 and convert it to gray code, what would I do? I would bring down the 1. Then I would do this guy right here. This is called an exclusive OR. I would say, right, let's see what I'm doing. I would take this one and do that. So that would be a 1 and a 0. A 1 and a 0 would give me what? Would give me a 1. Then I would go a 1 and a 1 would give me a what? 0. And then a 0 and a 1 would give me a what? 1. And then a 1 and a 0 would give me a what? A 1. And that would be the way we do the gray code. And this is what we call an exclusive OR, by the way. And we'll look at that. So here, if the inputs match, we get a 0. If the inputs don't match, we get a what? A 1. So that would be the gray code. If I was counting in gray code, so this is gray code. But it's a code. So the only way I would know it would be, in fact, we're going to, even on your worksheet, we're going to skip over these because the book does it wrong. But this would be a 0, and this would be a count of 1. How many bits changed? Okay. This would be the code for a 2. How many bits changed? This would be a code for a 3. How many bits changed? This would be a code for a 4. How many bits changed? 1. Yeah, see, so this guy right here was the only one that changed. That guy changed right there. This would be a code for a 3. How many bits changed? I mean, 5. How many bits changed? This would be a count of a 6. How many bits changed? 1, right? So what if I go from a 6 to a 5? How many bits change? 1. So the gray code, no matter how you count, whether you're counting up or down, between every count, you only have a 1 bit change, which means you don't have the propagation delay of 1 bit. But the problem is it's not a number system, it's a code. If you don't know how to do the exclusive OR, which can be done by a computer in a heartbeat, then you look at this, there's no way in the world you can convert this over because it's not weighted, it's a law, it's a code. So when you do that lab in your lab book and you get to the grade code section, you're just going to do what to it? Skip over it because the book does it right. He does it in nibbles. Instead of doing the whole 8-bit word, he does it in nibbles. He does the gray code on this nibble, and he does the gray code on that nibble, which is not the way to do it. You got to have the whole 8-bit word to do the whole gray code on it. So it's counting code. It's high-speed counting code. How many bits change per count? 1. Do you have to be able to convert it? No. Alphanumeric codes. ASCII code. This guy is still used all the time in PLCs. So we have to be able to represent letters. We have to be able to represent numbers. We have to be able to represent symbols. So the first code that came out with, it's been around for years. It's called the ASCII code, and you've got an ASCII code chart there, right? So flip your number system over, and you should see an ASCII code chart on the back. So notice it says in rows and columns, right? You understand that? So the columns are your most significant digits. The rows are your least significant digits. And then usually the ASCII code chart is set up. Is this one set up in hexadecimal? I don't remember. So it's giving you the actual binary patterns. Yeah, but look down the rows. Yeah, it's hex. It's just that they only have 7 columns. I mean 8 columns. Yeah. So if I was going to send my name, Rich, I'd find R, an uppercase R, right? You understand that? And then I would look. You understand that? And then I would read the column first. What column is it in? 5. What row is it in? 2. So it'd be 52. The actual code would be this. So what they're doing is the chart is laid out in hexadecimal, but the code is a binary code. And why are they using hexadecimal? Just makes it easier to read, right? You okay? What's a lowercase I? Find a lowercase I for me. 69, base 16. What's a lowercase c? 60 what? 63. What's a lowercase h? What if I wanted to put an exclamation mark past my name right there? An exclamation mark. What would that be? 21. 21? Or can y'all do y'all's name in hexadecimal? I mean in ASCII code? Now you got to remember, it's a binary code, but the chart is laid out in hex. Y'all understand why? Because it makes it easier to watch, easier to read. By the way, these are control codes. Did I give you all the control codes? Yeah, we got to be able to control stuff. Start of text, end of text, start of header, start of acknowledge. We use these guys too. We use these guys a lot to we have an acknowledge and we have a not acknowledge. And we can ring a bell. We can do a backspace. We can do a line feed. We can do a vertical tab. We can do a form feed, a carriage return. What's some of the device? These DC codes. These are usually software. In the transition block, yeah. So we can send a lot of different things to tell the receiver when to do a carriage return, when to do a line feed. So used to the old on the old printers, this is what we had to do, you know. So this is the 7-bit ASCII code. Why it's 7 bits is because of something called parity. I don't know if we talk about that in the textbook. American Standard Code for Information. And so when the internet first came out, this was it. It wasn't actually a programming language. It was a formatting language. We call it HTML, Hypertext Markup Language. And this is basically you did the whole web page in ASCII. And you'd use a P and you'd put a code and it would tell it to do a paragraph. And every once in a while, when you look at this stuff, you'll see a percent sign 20. That's if you look at a 20 on there. So look at the column, column 2, row 0, and that should be the code for a space. And you'll see it pop up every once in a while if you ever look at the text. If you ever look at the HTML, y'all know y'all can look at the source code on that. But the problem is eventually what happened to the internet? Well, the ASCII code is the American Standard Code for Information Interchange. So the only language it supports is the Latin alphabet. So they had to come up with some other code that supports what? Other languages. So what code does Microsoft Office, what code does the internet use? No, that's the keyboard. QWERTY is the keyboard. You know why it's called QWERTY, right? Because it's Okay, so I'm gonna put in a new slide, and then I'm gonna come up here, and I'm gonna insert, and then I'm gonna come over and insert a symbol, and right down here, so I can blow it up. Can y'all see it? Right here it says, can y'all see the code? Unicode. And guess what okay, I'm gonna come up here. This is an uppercase A, and it says the uppercase A the Unicode for an uppercase A is 41. Look at your ASCII code chart and look at column four, row 1. What do you see? You see a capital A. So what they do, if you look at, let's go down to a lowercase. So an uppercase R. Look at column 5, row 2. So Unicode is a subset. The ASCII code is a subset of Unicode because if it didn't, it could support the other websites, right? You understand that? But Unicode is 16 bits. How many characters can I represent with 16 bits of binary? So take the base. What base are we dealing with? Base 2. Raise it to the 16th bit, 16th power. That's the way you can tell the number of combinations. What's 2 to the 16th? So in using Unicode, we could represent 65,536 characters, which is basically every written language out there. So that means we got, by the way, when you download these, they don't download all your character sets. I don't know if you've ever been to a website which says that you want to download the character set. It'll add that to it. Added so 65,000. They don't put the symbol for 65,536 characters in Microsoft Office because every character has to have memory right to take it up. But it takes quite a few. So so this is what the internet uses now. So now I can come down here and oops. So this is basic Latin. I can come down here, extended Latin. I can come down here, and this is, I think, some Greeks in here somewhere. Extension, space, modifiers, combined. So these are these Greek. So this is Greek. Now we'll look at that letter right there. So this Unicode is 042F. So there's beta right there. What's beta? Used to in the old days, we would use the uppercase B for beta. And there's omega, 3B2. So when you're typing all these characters on your screen, 90 words a minute, what is it actually using? It's using a code to represent those letters. And that's what's actually transmitted. So here's this keyboard. You can enter these codes directly, but this keyboard doesn't support it. So there's a Unicode for a Omega. And then also that we have Unicodes now for what we call the emoticons, right? You understand that? So every time you get a new set, but every time you get a new emoticon, it's actually one of these codes. So there's one for a smiley face, but it's not 3D. So we never could do that. Y'all remember how we used to do smiley faces? A colon with a parentheses, yeah. And then we use a nose where you, yeah. So not only does it support the alphabet, it also supports a lot of these codes. I don't know if we could see those or not because I hadn't downloaded this. And these are not supported yet. I don't know. I think you can go to Microsoft and download additional codes for your products if it's not supported. So this has I didn't go through them. It doesn't have 65,536, so that's Unicode. So it can be real big. Currently, the internet only uses 16 bits, but I don't forget how many. I think it can actually go up to like 32 bits. So I think your emoticon that you're using on your cell phone now is more than 16 bits. Okay, so that's Unicode. What other code did I say? Let's go. Oh, that's extended ASCII, which they call EBCDEC, but it's not EBCDEC, guys. This is EBCDEC right here, and this is it's a dead code. Nobody uses it anymore. It was actually used in a programming language called COBOL. You ever seen COBOL? We call it the green screen. We use it a lot. You ever seen when we register y'all? It pops up and it's black on white and everything's text. That's an old COBOL application. That's back before any graphics at all. It was all text. So, this is so the book says it's extended ASCII. This is extended ASCII. What extended ASCII is, it's actually an 8-bit code, and it adds a bunch of graphics characters to our screen. And this is actually true EBCDEC. Do you have to know this? No. Do you have to know Unicode? No. If you need Unicode, you look it up in a what? Chart. Do you have to know ASCII? No. If you need to know ASCII characters, you look it up in a what? Chart. Right. Gray code. If you need a good gray code, what I would do is I would type in gray code converter. I'd bring up the internet. I would type in my number, and it would give me the gray code for that. Because you got to understand this exclusive OR operation to actually do that. If I wanted to go from hexadecimal to decimal, I'd use calculator. The other bases that we're using, we primarily use them for what? To go between what? Binary and the numbering system. Because it's a lot easier for me to convey big, large numbers to you in hexadecimal or octal than it is to try to do it in binary. So everybody okay going from binary to decimal? Everybody okay going from decimal to binary? Everybody okay going from hex to binary? Octal to binary? If you had to do the ASCII code, what would you do? You'd use a chart, right? Even Unicode. Unicode, you can make charts for Unicode are huge. Uh, so usually, if we don't know it, we could go up and say, what's the Unicode for this? And it would pop up. I'll try to get y'all the Unicodes for those emojicons that's a pot. How many emojicons y'all have on y'all's phone now? Yeah, that's good. Answer a lot. Okay, but let me find this. And Derek left. I wish I'd have gave this to him before he left. I'll put it up on Blackboard though. This is kind of like the number system conversion that's going to be on test one. It's going to be a chart just like this. You saw one very similar to that in the digital. Okay, the digital. So y'all can kill two birds with one stone. Y'all see how this works. Yeah, so I give you the number in one base, and then you're supposed to do what? Convert it to. Oh, sure. Yeah. know why this thing ended. Write your first and last name. Go. Everybody okay? Y'all got your Esco chart right? Huh? First and last. Remember, you got to put a space between the two, right? Which is a what? It's a 20, right? Base 15. Base 16 will be okay. Yeah. That is the same thing you're giving out there. I know it is. Same. He gave y'all out this chart right here, too, didn't he? Okay. Oh, you wrote your name on it. And ask you code. Give me the code. I'm like, in this class. And then next Thursday in the class. Next week, huh? Y'all have to turn it down a lot. I'll explain that to you Monday. Yeah, we've lost one class in here. We can't afford to lose another. By this time, we used to be in lab. For motor control, you need tomorrow. Yeah, we're trying to do lab. We're ahead. We're ahead in that class. Okay.